chip. The work, published in Nature magazine, is the fundamental requirement for a revolutionary piece of hardware, the quantum computer.
With the copper powder,
team leaders Dr. Andrea Morello and Professor Andrew Durack and the main experimental author, Jared Plah, are based at the University of New South Wales in Sydney.
Modern computers store information as bits, which can be either 0 or 1 to create a binary code. These bits are realised using transistors or other devices on a silicon chip. Now, the power of modern computing comes from the fact that over the last 50 years it's been possible to cram more and more of these silicon transistors. So there's now over 1 billion of these on a single square centimetre of silicon on a chip.
now imagine you can make a bit that can be in the 0 and the 1 state at the same time. That's called a quantum bit or qubit. And the simplest example in nature would be just a single electron. It has a magnetic dipole called the spin, which is like the needle of a compass. But because it's a quantum needle, it can be pointing up and down at the same time. If you can make a computer that uses that, then you can program it in a completely different way. And you can solve certain problems that are otherwise impossible to solve on normal computers. For example, simulating and understanding molecules and complicated drugs, for instance. So you can actually design them on a computer instead of having to find them by trial and error.
So to build a large-scale functioning quantum computer, you need 4 basic elements. First, you need to be able to read information on a quantum bit, then write information on a qubit, then to take pairs of qubits and perform operations between them, and finally, transport information around the quantum processor to perform complex calculations.
To build a qubit, you must first insert a single phosphorus atom into a silicon chip, then build tiny electrodes just 30 nanometers wide above it. Each wire is 3,000 times smaller than the width of a human hair. Adding a small voltage to the electrode above the phosphorus ion forces an electron to cross the gap and orbit the phosphorus. That's the initialization stage, and the qubit is in a logic 0 state.
What we do to write information on the electron spin is to irradiate it with microwaves. The spin absorbs these microwaves and then begins to rotate around this sphere from down to up.
It can't stay tied to the phosphorus atom at spin up, so it drops back into the electron pool. This switches the transistor on, which corresponds to reading a logic 1 state.
What we have done now is to demonstrate the first 2 steps for a quantum computer: to read and to write information on a single quantum bit represented by an electron spin. But this is still done with the same technology used for normal silicon chips. The electron is attached to an atom that's implanted in the silicon, and the quantum information encoded on it is read out with a silicon transistor just fabricated next to the electron.
Silicon microelectronics and nanoelectronics underpins all of the information age at the moment, and if you can make a quantum computer using silicon, then you've got a fantastic advantage in terms of manufacturability. So the fact that we've now demonstrated a quantum bit in a system that uses effectively silicon transistors to read it out is a remarkable step, and it is going to very significantly accelerate the work in silicon.
I'm truly amazed every day that I step into the lab. I mean, on a daily basis I get to interact with this single electron which belongs to a single atom. We really are controlling nature at its most fundamental level, and being able to demonstrate the potential of this system for quantum computing, to me, is just